All right, welcome to the Explainer. Today we're going to tackle a question that sounds kind of weird, maybe even impossible. What is half a factorial? But trust me, the answer unlocks this incredible hidden corner of mathematics that shows up everywhere, from quantum physics to the stock market. So let's just jump right in with the puzzle. You probably remember factorials from school, right? 3 factorial is just 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. Easy enough. But what in the world is 3.5 factorial? I mean, how you even do that? How do you multiply a number by these half steps?
Right, so 3 factorial is simple. It's 6. But if we try to use that same logic for 3.5, we just hit a brick wall. You could try 3.5 times 2.5 times 1.5 times zero point 0.5, but then what? Do you stop? Do you go to negative numbers? This standard formula just isn't built for this. It's only for positive whole numbers. So right now, our puzzle seems to have no answer.
So think of it like this. On a graph, the factorials are just these separate dots. You've got a point for 1 factorial, another for 2 factorial, another way up high for 3 factorial, and so on. But there's nothing in between. The real challenge, the real mystery, is figuring out how to draw one single smooth curve that connects all those dots perfectly. And believe it or not, to find that curve, we have to take a little detour. So the key to cracking this abstract math puzzle, it's actually hiding out in the real world. Yeah, I know, weird, right? It all comes from how mathematicians model things that are uncertain and continuous. You know, stuff like the exact lifespan of a tire or the precise height of a person. In math speak, these are called continuous random variables. And unlike, say, flipping a coin where you get heads or tails, a continuous variable can be any value in a range. A light bulb doesn't just burn out at exactly 100 hours or 101 hours. Nope, it could be 100.3572 whatever hours. There are literally infinite possibilities. And this is where things get a little weird. Because there are infinite possibilities, the probability of any single specific outcome is basically 0. The chance that your tire gives out at exactly 50,000.0000 miles on the dot, it's essentially impossible. You can only really talk about the probability of it failing within a range, like between 50,000 and 51,000 miles. So, how do mathematicians deal with this? Well, they have this really clever tool called a probability density function. It's basically a curve with 3 simple rules. It's always positive. The total area under the whole curve adds up to 1, or 100%. And the probability of something happening in a specific range is just the area under that part of the curve. And here's the kicker, the really important part for us. To figure out those areas, you need integrals. You need a tool from calculus that's built to handle these continuous values. Okay, so what in the world does all this probability stuff have to do with our factorial puzzle? Well, that whole idea, needing a tool for continuous values instead of just these separate steps, that is exactly what we're looking for. We need to go from those disconnected dots to a smooth line. And to do that, we need to introduce the star of our show. And it turns out we're not the first to ask this. This is the exact same problem that had the greats, people like Leonhard Euler and Daniel Bernoulli, scratching their heads centuries ago. They wanted to find one single, beautiful function that would hit all the known factorial values, but also fill in all the gaps in between. Okay, deep breath. Here it is. The answer is called the gamma function. And I know that formula looks like a beast. It's an integral, just like we were talking about. But here's the thing. You don't need to worry about solving it. For us, what's really important is what this amazing formula does. You see, it has this one property that is just magical. The gamma of any number plus 1 is equal to that number times the gamma of the number itself. Now, if that looks familiar, it should. It's the exact same recursive logic behind the factorial, where 4 factorial is just 4 times 3 factorial. This one property is the key that makes the whole thing work. And look at this. This is where it all clicks into place. If you calculate the gamma function at n plus 1, you get exactly n factorial. You plug in gamma of 2, you get 1, which is 1 factorial. You plug in gamma of 3, you get 2, which is 2 factorial. Gamma of 4 gives you 6, which is 3 factorial. It's perfect. It hits every single one of those dots we talked about. Okay, but hold on, you might be thinking, couldn't I just draw any old squiggly line that goes through those points? And well, technically, yeah, you could, but the gamma function is special. It's what mathematicians consider the one true answer.
And there's a reason for that. It's all because of a famous proof called the Bohr-Muller-Up theorem. Now, what it basically says is that while, yeah, you could draw a million different curves, the gamma function is the only one that's perfectly smooth in a very specific mathematical way. It's the most natural, the most elegant way to connect the dots. It's not just an answer, it is the answer. So, with all that, we can finally go back and solve our original puzzle. Now that we have our continuous function, we just need to plug in 3.5. Remember, the formula is gamma of n plus 1 gives you n factorial. So if we want 3.5 factorial, we need to calculate gamma of, you guessed it, 4.5. And the answer is approximately 11.63. Boom, there it is. We found the exact point on our beautiful smooth curve, right between 3 factorial and 4 factorial. And the function just keeps on giving. It reveals these totally unexpected, beautiful connections in math. Get this, the gamma of 1/2, it's not some messy decimal. It is, for some d, that this function is plugged into the very fabric of mathematics. So you see, the gamma function is so much more than just a party trick for calculating weird factorials. It's a fundamental tool, kind of like a Swiss Army knife for mathematicians and scientists. And since it's the master of handling continuous stuff, it pops up everywhere. Seriously, we're talking statistics for modeling things like the time between earthquakes. It's in the equations of quantum physics, fluid dynamics, even in number theory, helping us understand prime numbers. It's just all over the place. So the big idea, the real takeaway, is that by trying to solve what seemed like a simple brain teaser, how do we fill in the gaps? Mathematicians built this universal tool. This one function helps scientists describe and calculate this huge range of processes, from the decay of a single particle to the distribution of stars across a galaxy. So, yeah, we started with a really simple question, right? What's half a factorial? And it took us on this incredible journey through probability and calculus and landed us on one of the most powerful and profound functions in all of science. And it just makes you wonder, doesn't it? If an idea this big was hiding behind something as simple as the factorial, what other beautiful connections are still out there, just waiting for us to find them?